Yes, thank you very much. So firstly, I'd like to say thank you for giving us this opportunity to present our work here today. And I'd like to thank also the co-authors of the review that I'll be presenting, which is Jonathan Henshaw, who is the lead author of the review, also Cara Battersby, Adam Ginsburg, Mattia Sormani, and Dan Walker. So as I said, I'll be presenting a review of star formation in the central molecular zone of the Milky Way, which may not be something that the majority of you do consider in your everyday research. So I'm going to start this by presenting and walking you through a relatively simple statement, and that is that the present-day star formation rate within the extreme environment at the center of the Milky Way is significantly lower than we expect. So this is quite a simple statement. I'm going to walk you through it, but the broad implications of this statement are wide-reaching. And this statement really came about around 10 years ago, around the time of the previous Protostars and Planets review, and has really spurred on the field in the last 10 years since trying to understand this statement, and that's why we wanted to write this review in the first place. So I'm going to walk you through this statement. I'm going to start with the extreme environment of the galactic center and why you should care about extreme environments. And then I'll talk about what exactly the galactic center is, so I'll get to that. So here's a plot of the star formation history of the universe. So we can see at a redshift around 1 to 3, there was a peak in the star formation rate in the universe. So the physical conditions at this peak of cosmic star formation, which was significantly higher than we see in the current day universe, could have been very different to what we see in the universe today. So understanding how star and planet formation varies at this peak of cosmic star formation in very potentially different conditions to what we're seeing in the universe today is extremely important. And of course, we're going to hear a lot more about that as we go through the next few days. The problem is that we can't see these high redshift systems, these extreme environments, in high detail and sensitivity that we need to study star and planet formation. They're just too far away. So we need a more local analog in which to study the star and planet formation in these extreme conditions. So I don't want to scare you. Here's a table from our review. But I want to just show here that this is the parameter space of the solar neighborhood that we just heard about. So this is the parameter space in which we know the majority of our theories of stars, how stars form, and subsequently how planets form, just because it's the environment that's closest to us and most easily accessible, like we just heard about. And this is an extreme environment, slightly biased, the galactic center, which I will talk about in a few minutes. But this is the environment which is potentially very extreme compared to these solar neighborhood values. And I just want to highlight several key properties here, and I will walk through this again later on in the talk, but just to show that the values I'm showing here for the galactic center are 1 to 2 orders of magnitude typically higher than we see in the solar neighborhood. So the galactic center of our Milky Way could be one of these high redshift extreme analog environments, but obviously a lot closer to us than these high redshift systems in which we can study star and planet formation. So back to my statement. The galactic center, what is it? So here's this top-down image, what we think the Milky Way might look like. Some caveats here, of course, we just heard about. But this is our solar neighborhood, give or take. It's around a few hundred parsecs around the sun. And this is the galactic center. This is the central kiloparsec or so of our Milky Way. And there's several interesting features within this central kiloparsec, which I'm now going to discuss. So firstly, within the bar, this is situated within the bar. You can see here in our top-down image as well, these dust lane features, and these are regions of molecular gas inflowing towards the very center of our Milky Way from the spiral arms, from the bar ends. And this has been measured at a rate of around a solar mass per year. And as the gas flows in, it falls within this central region, which I'm going to call the central molecular zone. And the central molecular zone contains around 5 times 10 to the 7 solar masses of gas. So this is around 10% of the entire Milky Way gas, molecular gas reservoir. And this is why it's called central, because it's in the middle, molecular, because it has a large amount of molecular gas. And we think this central molecular zone, as you can already see here, and maybe see a little bit up there, that it has this ring-like structure. And indeed, we see this in nearby galaxies as well. We've seen some images from the FANGS survey already from JWST, and you can see here some more galaxies, and you can see these central regions at the end of the dust lane features, they all have this kind of ring-like structure, which we also think the central molecular zone of our Milky Way has. There's some discussion of the exact structure of the central molecular zone, but suffice to say, this is around 100 parsec in radius ring in the galactic center. And we do go in more detail, of course, in the review on this point. So this is all well and good, but that's obviously the top-down perspective that we see. We don't actually see that, we see this. This is our line of sight through the galactic, the Milky Way. And the galactic center can be seen in the center there. So obviously we have to peer through this dust and this extinction to see the galactic center. And to do that, we have the infrared and the radio. So this is the central couple hundred parsecs, few hundred parsecs of the Milky Way. And this is the central molecular zone. So already you can see some quite interesting features here. For example, in the radio, which is the red, we can see outflows, these large-scale outflows from the galactic center, potentially caused by Sagittarius star, potentially caused by star formation, feedback. We can also see supernova remnants, H2 region complexes there on the left-hand side. We can see highly attenuated dense gas clouds here along the line of sight. And these are attenuated up to the mid-infrared, so extremely high column density, extremely dense molecular clouds. We can also see very bright, compact, and extended regions of active star formation here. And within the very central 50 parsecs or so, we can see several other interesting features. On the upper left, maybe not so clear here, but you can see other dense gas clouds seen in extinction. But we can also see clusters, the Arches and quintuplet cluster here. So these are young, massive clusters, around 10 to the 4 solar masses. And of course, Sagittarius star, which lies at the very center of the Milky Way galactic center. So a lot of interesting physics going on within this environment in a very close, compact vicinity. So back to my statement, the star formation rate. So how do we measure this? The star formation rate here within the galactic center. And again, I don't want to scare you with this table, but suffice to say there are several different ways in which we can measure the star formation rate within the galactic center. Because it's quite close to us, we can do the traditional ways that you would do in more local solar neighborhoods, such as YSO counting. But also we can use integrated light measurements because it's quite a big area on the sky, which you would, for example, do, which the extragalactic community does. I just want you to focus on this bottom value here. So over the last 5 megayears or so, which is the value on the left here, the star formation rate is of the order 0.1 solar masses per year. So that's around 10% or so of that inflow mass, if you remember back to earlier in my slides. So just to summarize, the galactic center, this very central region, has around 10% of the molecular gas of the Milky Way, hence why it's called the CMZ. Has around 10% of the galaxy's star formation, but this is an extremely small region if you take in context the whole volume of the Milky Way. So 0.01% of the volume of the entire galaxy. So within this very small region, you have a very high concentration of star formation and gas. And this is not only critical for our understanding of then star and planet formation, but in general, more galaxy evolution. This is an extremely, extremely interesting region for several reasons. So, but that said, I'm saying here high star formation density. I say here low. So here in my statement, I've said the star formation rate within this region is significantly lower than expected. So what do exactly I mean by this last part of my statement? And this is where this comes in. So this is the very famous Gauss-Solomon relation. So this is the star formation rate as a function of the dense gas mass. So it's somewhat similar to a Kennicutt-Schmidt-Wright relation. But here focusing on not the molecular gas, but the dense molecular gas. So this is dense gas above a density of around 10 to the 4 per cubic centimeter. And here we see a tight correlation, and that extends over several orders of magnitude, both within the Milky Way to nearby galaxies and even more extreme systems. This basically highlights that in this picture, the fundamental driver here is just the physical amount of dense gas you have. So above a given threshold, not much of the physics really cares about your star formation. Basically, just the amount of dense gas you have goes into the stars. Obviously, there's some scatter here due to observational uncertainties, but also second-order effects on then the conditions. But the main primary effect here is just the physical amount of dense gas you have. But the problem here is that for the CMZ, we have similar measurements, and if you plot the CMZ on here, you can see that this is a major outlier. This is a factor of 10 to even a factor of 100 lower than you would expect. So the star formation rate per unit dense gas mass is significantly less within the galactic center. And that poses a problem here, of course. And we can see that in resolve studies. Obviously, that was a single point I was showing in the previous plot. But in high-resolution resolve studies, I'm not going to go through this in too much detail, but suffice to say, again, that we do see this. We see that the stars that are forming in the galactic center only form in the relative overdensities, not at a given threshold of 10 to the 4, but the relative overdensities which are even higher than 10 to the 4 within the galactic center. So there's a problem here. Those fixed thresholds for star formation just don't seem to hold within the Milky Way galactic center. And that's a problem for our understanding for star formation. So then, as I said, this statement came around 10 years ago, so that was kind of the state of play that was coming in around the time of the previous Protostars and Planets review. So since then, we've really tried to push to try and understand this problem, to try and understand how to solve this problem. And the kind of overall picture is that we need to understand the galactic center as an ecosystem to really understand this. So what I mean by that is the galactic center is not an isolated system. The star-forming regions you have in the galactic center are not isolated themselves either. So we need to understand how the galactic center fits into the global picture of the Milky Way in terms of inflow, in terms of outflow, in terms of evolution. And then we can go on to understand how that picture, the inflow, the gas, the dynamics, etc., coming into the galactic center is affecting the extreme conditions that we're actually seeing in the galactic center, and how those extreme conditions then affect the local sites of star formation. So I'm just going to start with this first part here and just give you an overview of several efforts to understand where the galactic center fits in this global picture. And then I'll talk more about this second part in more detail. So again, we can go back to our table to try and understand this. So we can have averages over a few mega-years, but we're going to also have longer-term averages of the star formation rate as well. And these have been measured for the galactic center. And we see that on average, this is around a 0.1 solar masses as well. So over a kind of 100 mega-year timescale, the star formation within the galactic center is more or less similar to what we will see today. But the problem is that we know there are several, as I pointed out at the beginning and now tour of the galactic center, several regions, massive clusters, for example, where we know should have formed in the last few mega-years, which should have had then potentially higher star formation rates to study in the past, to form in the past, sorry. And this can also be seen if we look at the star formation history of the galactic center. We can see here over the past giga-year or so, if you convert these star formation histories from the stellar populations within the galactic center, that the star formation rate could have been factors of a few higher than to even an order of magnitude higher in the past than the current day star formation rate. So if you remember the current day star formation rate, 0.1, so these are quite significantly higher in that sense. So then the star formation rate could have varied, the amount of gas in the galactic center could have varied, of course, if you had this inflow. So understanding how the star formation rate, the amount of gas, and the properties of that gas as a function of time is extremely important. And of course, simulations have tried to investigate this. I'm not going to go into huge detail here, but I'm just showing two simulations here. There's a lot of further reading if you're interested. Two simulations that posit different mechanisms for driving the variability in the star formation, be it that internal, so feedback within the galactic center, altering the star formation rate, forcing outflows and accretion, or larger scale dynamical effects, for example, that bar, the dust lane feature, feeding the galactic center at a variable rate, which could then vary the star formation as a function of time. And here I've matched the scales on these two plots, and you can see that we do see in the simulations variation. The variation varies in terms of magnitude, but also in terms of how often and the significance of that. So There's still work to be done here, and we are looking into this, but this is a key piece of the puzzle to really understand the galactic center as an ecosystem to understand star formation. Now I'm going to focus on the second part of this, which I think is more relevant to the interest here, and that is then how these extreme properties that I've mentioned go into affecting star formation. So I'm going to focus again on parts of this statement, and first of all, the extreme conditions. So how extreme are we really talking? So going back to my table, as you can see, factors of 10, 100, what does this mean? So I'm going to walk through that table and walk you through some of these properties. So first of all is the stars and the gravity. So we know that the stellar potential within the galactic center is 1 to 2 orders of magnitude higher than within the solar neighborhood. This means that there's a significant number of field stars per unit volume within the galactic center. So 1,000, 10,000 even field stars per parsec cubed within the galactic center, which are going to have a large impact on the dynamics of molecular clouds, the boundness of molecular clouds, the dynamics of any planet star-forming system that you have within this environment, just to the sheer number of potential interactions that you can have just due to these field stars. But also that, the pressure, the weight of the environment is significantly more as well, which is going to have a huge impact on the dynamics across this region. The magnetic field is much higher, so 1 to 2 orders of magnitude higher. These are still relatively early results, but large scale do show this. And I think there's much more to come in this direction. But obviously then this could have, these higher magnetic fields could have an impact on gas flows around the galactic center, gas flows towards Sagittarius star in particular. It's been seen in the simulations recently. But also, of course, the magnetic field would have a large impact on the dynamics of any star-forming system within the environment as well. The gas is denser. So to make the point here, I previously mentioned that it is dense. More or less all the gas within this region is above a density of around 10 to the 4 per cubic centimeter, whereas in the Milky Way neighborhood, this value is more like a few percent. So all of this gas within this environment, that significant reservoir of molecular gas I was talking about before, is above this 10 to the 4 per cubic centimeter, so extremely dense. I just want to put that in context. So if we take this and compare to and look at, for example, the brick molecular cloud, so this is one of the densest, most massive molecular clouds, not only within the galactic center, but within the entire galaxy. And this doesn't show any signs of widespread, at least, star formation. So this is the brick cloud here. So this is around 5 parsecs in size, as a mass of around 10 to the 5 solar masses. So if we compare that to Orion that we've just seen, then this is the comparison. So here, I've not only matched the spatial scale, but also the mass scale. So the mass in this little tiny thing is the same as the mass in this region of Orion. So somehow the galaxy within the galactic center has allowed the formation of an extremely massive, extremely dense molecular cloud within this environment. So not only that, the gas in this environment is also warmer. So this is factors of a few up to an order of magnitude warmer than we see within the solar neighborhood. So we're talking about 50 to 100 Kelvin in the gas. And also not only that, the dust temperature is higher, but not as high, factors of a few. So you can imagine this is going to have a huge influence on the properties of any star-forming region, the chemistry within any star-forming region within this environment. The origins of this is not particularly clear. Potential are mechanical heating, but also cosmic rays. Cosmic rays are a lot higher here. So again, 1 to 2 orders of magnitude higher in this environment, which could be then leading to that higher dust temperature, higher gas temperature. And also, of course, this is going to have a large effect on any chemistry across the region. The origins of this are not completely obvious, but you can imagine, given our tour of the galactic center and showed all the high energy supernovae, Sagittarius star, H2 regions that were in the environment, it's not hard to imagine that they could cause this elevated cosmic ionization rate. So that could affect the chemistry, as I said. So the chemistry within this environment, what we're seeing from molecular lines is very different to what we see within the solar neighborhood as well. So we're seeing extended shock traces within this environment. We're seeing extended dense gas traces within this environment. So gas traces such as HNC, HCN, HCO+, N2H+, for example, within local regions would be isolated towards the cores, so the star-forming parsec scale cores, for example. Within the galactic center, we're seeing that they're extended across hundreds of parsecs. And for example, here we're seeing that in the N2H+, I'm just showing the N2H+ map, and you can see how that's extended across the entire galactic center, more or less. But not only this, we're seeing, if we zoom in on some regions, SAGB2, for example, you can see that these are extremely chemically complex. And SAGB2 is, if not one of the most complex regions for chemistry in the entire Milky Way. I looked just before this talk, and there's around 290 molecules that have been detected in the ISM, and the vast majority of these have been detected towards that SAGB2 core, that SAGB2 molecular cloud. So this is an extremely interesting region, the galactic center, and the clouds within the galactic center for very complex chemistry. And much more to come on this, of course. I really like the line from our review here on this point. I don't know who was responsible for this, but molecular lines in the CMZ are bright, and so is their future. I think there's much more to come in this direction. So we can obviously do a lot of interesting science with molecular lines, and one of those is investigating the line width and seeing how that varies as a function of scale. So this gives us the line width size relation that I'm sure you're all very familiar with. And we see again that the galactic center on fixed size scales is much broader than molecular disk. So molecular disks here, you can see in green, you can see the blue points are significantly higher than those disk values on parsec and larger size scales, that is. On the smaller size scales, you can see that they're actually more similar. So this is very interesting that you have this very steep decline, potentially. So open questions here, of course, is this line width entirely related to turbulence? How is this turbulence replenished if this is the case? And then how does this turbulence cascade down to the smaller scales and affect your sites of star formation? And I'm going to come back to this last point now. So this brings to the second part. How do these physical conditions, how does this environment affect the way stars and planets form across the CMZ? So there's been a lot of work in this direction trying to understand, first of all, the prestellar core phase, and obviously ALMA has done a lot of work here in the past 10 years on this. And the kind of overall picture here is that on the size scales of the cores at high resolution, you can see here the radius is a function of mass, so the density of the cores are very similar to the cores that we're finding within the Milky Way disk. So the points here from the disk and the CMZ, it's quite difficult to tell the difference. And linking to what I said before about the line width size relation, again on the small scales being very similar to the disk, this could point to the fact that once we have collapse, once we have bound cores forming within the galactic center, they actually appear to be quite similar to what we find within the disk. So which is interesting. So the star formation may not be inhibited, more the core formation within this environment may be inhibited, causing then the lower star formation rate in a sense. So once the cores are formed, it's interesting to look at the clusters to understand the physical conditions in which those cores, the star formation, is actually going to happen. And to do that, we have two very massive young clusters, the arches and quintuplet cluster, which are very young, 10 to the 4 solar mass clusters within the environment that we can go to. And there's two things I want to point out here. So the first one, quite controversial, but there is evidence to show that the initial mass function within, I think this is the arches cluster, is significantly shallower than the solar neighborhood, highlighting that more massive stars could be forming and present within the galactic center due to its extreme conditions, potentially. But not only that, the fraction of clusters formed within the galactic center could be much higher. So here I'm showing the fraction of clusters as a function of the gas density, surface density, and you can see that there are factors of several higher than the solar neighborhood. So together this highlights that within the galactic center, one, you could find and form more massive stars, and two, the stars that you are forming per unit solar mass are more likely to be situated in a clustered environment. So obviously then these massive stars, this clustered environment is going to have a huge impact on any star-forming region, disk-forming region, or planet-forming region that you may form. And indeed we're, okay, good. So indeed we're pushing in this direction to understand this, and of course going to the next stage of star formation is the natural step here. So going to the protostellar phase, and we're pushing to high resolution with ALMA, high sensitivity with ALMA to study this, for example. And here I'm just showing some very recent examples over the past couple years. In fact, you can see the references here, 2021, 2022. So over the past couple years even, we've only just been recently able to find, detect these outflows across the galactic center, where we can then use to study the dynamics, the environment of these very young star-forming systems. And of course, we can do that. We've only just started to find these things. You know, obviously, it's still very early, but we have already followed up on this. And indeed, we find evidence for at least one protostellar accretion disk within the galactic center, which is very exciting in the past year. So this is the first evidence for such a disk. This is within the SAG-C region. And this disk here, you can see is a Keplerian disk here. But not only this is really interesting. You can see this has several companions and an interesting spiral-like structure, potentially induced by the interaction with these companions. So not only this first very interesting protostellar accretion disk has been found, but also this protostellar disk has been found with some signatures of interaction potentially linked to that highly clustered environment. So this is very exciting, and I'm sure a lot more to come in this direction soon. And then the last stage is, of course, the formation of planets. This is still extremely early at the moment, but I just want to walk through some theory of why this might be interesting. So I'm just showing a plot here from Winter et al. And on the x-axis, you can see stellar density. So with increased stellar density, you're obviously going to get more interactions, dynamical interactions. On the y-axis is radiation field. So with an increased radiation field, you would get more photoevaporation. So basically, as you move up and right in this plot, you get shorter disk lifetimes. So this is what these different lifetimes are showing here. This is skipping ahead. So this is what we see. So the parameter space spanned by the solar neighborhood on the left first, you can see in dark, is towards this kind of lower left corner of the plot, highlighting the disk lifetimes of a few megayears or so. In the galactic center, everything's pushed up to the upper right. So the take-home point here is that the disk lifetimes, because of primarily the photoevaporation of the disks, is significantly shorter, factors of several shorter than we would see potentially within the solar neighborhood. And we do see signs of this in the mid-infrared excess, highlighting lower disk fractions within the galactic center. So there are some observations in this direction already, but still a lot of work to do here. But the summary is that this could be a very interesting environment to push planet formation, disk formation in the next few years. So I just want to go to my summary now, and again, linking to my statement from before, which was around 10 years old now, that the star formation rate is low within the galactic center, or lower than we expect. And to understand that, we have to study the galactic center as an ecosystem. And that ecosystem starts with the large scale, so understanding how mass is concentrated towards the galactic center and essentially feeds the galactic center, and how then processes within the galactic center can affect that, potentially forming outflows, and those outflows can extend up to several kiloparsecs even, so significant outflows seen here as well. And then inside of this, linking that to the extreme conditions. So the extreme conditions within the galactic center have a global effect on all stages of star and planet formation. But then starting with the early stages in the clouds, we see the magnetic field densities, chemistry is much higher, which then affects the formation of the cores. When the cores do form, they form similar to potentially what more local regions form as. However, we get more massive ones, we get more clustered environments, and those clustered environments then will produce more feedback, and that feedback will put energy back in terms of H2 regions, various effects of supernova effects, for example, that Mark discussed. into the environment, which will then kind of self-cycle and form more extreme conditions in the galactic center as well. But not only that, obviously then within these stars, within these clustered environments, you would have potentially a strong radiation field dynamics, which is going to affect the formation of disks, accretion disks, planetary disks, and subsequently planets. And I think then linking to the last point here, how does this affect us? How does this affect the implications for life? How does this affect the formation of, for example, solar system bodies? I think all of this together is extremely interesting then if you push to the context of these high redshift systems, maybe not a redshift of 2, but a redshift more like the one in which the sun formed. I think is extremely interesting. Of course, I've highlighted throughout this talk several key avenues for the future, and I think there's a lot to be done here from observations, from ALMA, from large surveys from ALMA, for example. ACES is one of these such surveys. But also the SK and VLA is doing a lot of work in this direction, higher resolution observations of the star-forming regions. Of course, JWST will have a high impact here, being able to peer through the extinction in the infrared to study these regions at high resolution. I have a slide on that in a second. And on the theory side, of course, global simulations, understanding the dynamics, but also zoom-in simulations to understand star formation, the chemistry, and then allowing direct comparison to the observations is something that we're really pushing towards, which is extremely difficult at the moment, understanding all of these different effects and how they essentially translate within the simulations to give real observations. So I can't end. I promised JWST. So here's the brick cloud. This is what we have when we were writing the review. This is what was the state of play around the time of the previous review. Okay, maybe it's not huge on this screen, but not a huge amount of detail in that. And this is what we're seeing now with JWST. So you can see a huge amount of detail in the extinction here around the molecular cloud. You can see a lot of interesting structure. You can see a lot of interesting structure in the background. You can see star-forming regions here nearby this brick molecular cloud and the detail that you can see there as well. And this has been stellar subtracted, so there are a lot of YSOs and other interesting sources within this image which you can't see, but of course this is going to allow in-depth studies of those as well and really constraining both how the molecular cloud evolves but also how the young YSOs evolve as well in this environment. So I hope I've convinced you that the CNZ is interesting. It's an extreme environment that you can put your stellar system, your planet-forming system in, and understand how it evolves in a more high extreme environment. And if that has interested you and you want to get your hands on some data, we have an online directory here listing various data sets which you can go yourself now and download quite simply. So if you want to look at a CO cube for a molecular cloud, or you have some interesting chemistry and you want to know what lines have been detected where and what they look like, you can simply go here and we have listed all the data sets available. And also, if you want to hear more details about anything I've talked about during this talk, we did hold a talk series ourselves in preparation for this review where we had several experts come talk about the various things I've discussed. So if you want to hear more details, I would urge you to go to this website and watch these talks. I think they're on YouTube, so they're available. And with that, I'm going to leave my summary slide up here and yeah, take any questions. Thank you very much.
Thank you, Ashley. So the chapter is now open for discussion. Doug?
Yeah, Ashley, that was a great talk. Thanks very much. Over here, to your left, I think. There we go. Cores, when they get bound, gravity matters, so I might imagine they'd all be the same, but temperature also matters. Mm-hmm. And so I'm wondering, and the pressure mattered in whether you got to be bound or not. So I'm wondering about two things. Are the temperatures dropping when you get to these cores so that they're getting more like the temperatures in the disk, or are the temperatures still high, and that's the gas temperature? And then secondly, are you seeing any evidence that you're getting bound objects down to even smaller? Because the high pressure should allow for that.
Yeah, no, that's a good question. So, yeah, we do see that the temperature does drop towards the bound cores, and the gas temperature, and in fact the dust temperature, when you get to densities of around 10 to the 7 or so, when you get to these high density cores, then they do, at that point, become similar. So we do see that. I can't remember off the top of my head exactly how that compares to disk environments. It's hard to imagine that you would get, sub 10 Kelvin like temperatures that you would within a disk environment, for example. I think that would be quite extreme. So that obviously then has implications for any deuterated chemistry and interesting things like this. In terms of the lower mass cores that you're finding, there's definitely cores that are low mass across the region. If they're bound or not, I suspect they're kind of borderline bound. So they are there, just the sense that the samples that we have, particularly at resolutions needed to study them, and the sensitivity you need, the resolution that you need to study them, are lacking at the moment, and that's really where surveys like ACES are coming into play at that point, and to really understudy those in full detail. So I think the field's heading in that direction for the low mass, for sure.
We are going to take a question on the other side.
Thank you. Very interesting talk. So I'm just curious about the circumstellar disk you found at the Galaxy Center. So as far as I see, that's the radius something like 2,000 AU, which is more than 10 times larger than what we see in a nearby star forming region. So I was just wondering whether you could expect such a large circumstellar disks at the Galaxy Center, or probably you see the more stars inside, or you cannot just resolve that yet. Do you have any comment on that?
So my first comment is that this isn't my work, so I don't know the full details of that work. I suspect that the resolutions are really being pushed in those observations. I think there were something like 0.01 arcseconds or so, very high resolution observations, or maybe not that high, but very high resolution. So I suspect that they are pushing the resolution that they have. So indeed, on the smaller scale, this may have a slightly different radial profile than several thousand AU that you have here. A point is that this is a very massive disk. If I remember, it was a few tens of solar masses, or around 10 solar masses or so. So this is a very massive disk around a quite high mass star system. So I'm not an expert in the disk field, but maybe you may expect towards more massive stars, more larger disks in that way. So potentially, yeah, I think, again, this is a first detection. So I think in future there will be more to come on that point as well.
Okay, thank you.
Thank you.
There is a question in the back.
Yes, very nice talk. My question might be very similar to the previous one, which is about the possible protoplanetary disks forming in the CMZ. You mentioned that the extreme environment affects the disk lifetime, shortening it to about a megayear. I understand that you don't necessarily have the resolution to see on the size scale, but is there some theoretically expected protoplanetary disk size corresponding to that extreme environment?
Also a good question. I would have to defer that to a more planetary disk forming expert. I'm not a disk expert, so I wouldn't be able to answer that. I can definitely look it up for you though, thank you.
Mikael?
Great talk, actually. You mentioned it in one subclause, the connection to the conditions at the time of solar system formation. So can you maybe elaborate to what extent is the CMZ maybe a better laboratory or a worse laboratory to present-day star formation regions?
Okay, so this is a tricky point. When I say the conditions are very similar to the high redshift systems, this is from a work that specifically looked at, for example, the line widths, the density, the stellar surface density within that environment. It's just somewhat similar to what you would expect at a redshift 2 or so. Of course, we have a higher metallicity within the galactic center, which is a big difference. These higher redshift systems may be forming stars more efficiently than we see within the galactic center. So I think the point is that here, it's difficult to directly link the galactic center to these high redshift systems. It's definitely extreme than you see within kind of a more local system. How that directly links to then redshift of 2, redshift of 0.5, like the sun would have formed in, you can imagine, you can maybe expect that the system was particularly different then, but directly linking to that is kind of tricky. But I think this is an interesting direction to go to really push beyond what we see within the local environment, because as I said, regardless of this is high redshift or not, this is extremely important for galaxy evolution and contributes significantly to many of the stars that we see in our own galaxy, just because of that high star formation rate comparable to like the rest of the Milky Way. So I think the high redshift angle is an interesting angle, but in terms of galaxy evolution and the stars we see, it's also fundamentally important to push to extremes in that way as well.
Question over there?
Yeah, thank you. I have a question on the relative flatness of the Arches cluster mass function you mentioned. It has been a discussion over the last 20 years or so.
Yeah.
Whether or not it's dynamically induced by mass segregation, the cluster is relatively old from a dynamical perspective, or that it is relatively flat. Can you comment on that?
So obviously the galactic center is going to have a lot of dynamical evolution effects, just due to the tidal stripping as you orbit the galactic center, as the cluster interacts with the various molecular clouds. Of course, you're going to get some dynamical effects there, which is going to induce stripping, remove some of the low mass stars potentially from the cluster. We do see that there are signs that these clusters are extended across the galactic center, so both the arches and quintuplet, you can see they're very compact, parsec or so in size, but you do see large-scale tails across the galactic center associated with them, so they're obviously losing stars, similar to what we saw in the previous talk, for example. We do see that within the galactic center. My knowledge
I guess my question is the flatness of the mass function intrinsic or is it induced?
I don't know. So I think that's again not my field of expert, but yeah, potentially. I mean, it's the extreme conditions of the galactic center are where you want to push to find such things. The high gas densities, the high pressures are where you may expect such effects to be. I did say this is a controversial point when I introduced that plot. So yeah, there's still some debate. It's been 20 years, but yeah, still some debate on that point, of course.
There is a question in the back. Yes.
Me? Okay. It's kind of following on with the IMF stuff in the CMZ. You get a lot more massive stars. I was curious, do we know much about the multiplicity of the massive stars in the CMZ? Because I'm not an expert on the pistol star, but I know that from what we know, it's a really massive star and looks like it's single, and I'm wondering whether the massive star formation pathway is significantly different in the CMZ compared to the field, because most massive stars have companions, whereas the pistol star doesn't seem to have one. So I'm just like, are the other massive stars in the CMZ also singles, or do they have companions?
So it's a good question. So I can imagine so. I don't necessarily well, maybe some dynamical effects could have, like I said, a lot of the field stars around could have an effect on that, and a more clustered environment could have a general effect on that point as well. I'm not familiar with the literature on this too much, but yeah, I can imagine. I wouldn't see why that would be a major effect and why they wouldn't. But again, I can look into this in more detail, of course. Thanks.
Yeah.
Hi, Ash. Thanks for the talk. So you have mentioned here how the mass may be transported towards the central molecular zone.
Yep.
I was wondering if you could comment something on how the mass from the central molecular zone, that seems to be a ring, could be moving into the central part where the black hole is, for example.
Yeah, no, absolutely. So I think this is a very open topic at the moment, obviously extremely important for understanding how the black hole grows, the central nuclear cluster grows. I think from the simulation point of view, this was not entirely clear until relatively recently, and I think that's due to the different feedback. The magnetic field have both quite a significant effect on this. So the feedback from supernovae from H2 regions, making the gas lose momentum, and then allowing the gas to fall towards the center, or the magnetic field lines being such that they can facilitate flow around the galactic center and facilitate flow towards the very central, the supermassive black hole. So I think they're the two main lines at the moment that the simulations are following. There was a recent paper, Moon et al., looking at this, if I remember, from the magnetic fields, and Mattia, Sormani, and Cara looking at this as well in their simulations. So I think there's more answers to come from the theory side on that point. From the observational side, of course, we're, as you know, pushing in that direction as well, but it's very difficult to disentangle the 3D structure. But there is efforts to do that for the 20 and 50 kilometers a second cloud, of course, as well.
Yeah, just a comment and question. First of all, thanks. I mean, quite a very interesting, almost exhaustive review on the CMZ. Coming back to this posing question about the IMF of the CMZ zone, which is, as you showed, I mean, there are a few hints pointing to something which is flatter than saltpeter. But I mean, there is a person who raised quite a very interesting question 2 minutes ago about the tidal effects. And I will certainly argue that there is, whether it's the explanation or not, I'm not sure, but definitely tidal effect near the central molecular zone plays a crucial role. Because you mentioned the external pressure density or surface density and the Larson relationships, which still, I mean, you do follow a Larson relation, but the normalization is much higher, because meaning that turbulence is larger, density is larger, which is exactly, temperature is higher, which is exactly what we find in massive early type galaxies. And as you know, there are several, concluding results pointing to an IMF in massive early type galaxies, which is bottom line. It's much with a peak which is around 0.1 solar mass. And a plausible explanation, which we suggested with Patrick and Bell and Phil Hopkins as well, will be that it's a direct consequence of density and turbulence. Yet it's exactly the opposite for the central molecular zone, exactly as you showed. Strangely enough, I mean, it points towards a top-heavy IMF. And if you write the Jeans equation, I mean, just first order, if you include the tidal fields in the Jeans equation, you show that the density profile points, I mean, you obtain a flatter IMF. It's not a proof again, it's just a suggestion. But I would definitely think that the tidal, we know that there is a lot of shear near the, I think Mark and Krishkin wrote a paper about the CMZ a few years ago. And so I would argue that it's definitely something to nail down.
Yeah,
because if you change the potential, it might be a plausible explanation. Whether it's connected or not with the SFR, I would argue that it's also, the SFR is also a consequence of that. But it's just, I'm waving hands.
No.
Thank you very much.
Absolutely, yep, thank you. Do I have time to elaborate on that? Or is that? Yeah, I mean, so, yeah. I think the key point here, building on the previous question, is if the IMF forms like this beforehand, or if this isn't a case of evolution, right? So I think nailing down, both with observations in the radio, for example, looking at core population statistics and understanding if the IMF does form like this is one thing. We obviously need the resolution sensitivity for that. But understanding the dynamical effects and the evolution of these things in the galactic center, where these clusters are very massive, very dense, very bound clusters, but they don't last for very long because you have such strong tidal effects. So we know that these clusters are much shorter lived than the young massive clusters that you expect to see in the disk. So nailing down how these two things affect what we're seeing is definitely where we're heading in the field, for sure. Thanks.
Good. Thank you again, Ashley. I think.
Thanks, everyone.